I'm very happy to present here the work we are doing at École Normale Supérieure with a few people, which is about low-dimensional representation of physical field. And actually what we want to do at the end is to build a statistical model for non-Gaussian physical field. So first, I won't exactly explain what are physical fields in terms of a precise definition, but here I gave to you several images from standard classification tests in data science and images that we have in physics. That's the kind of field we want to investigate and to statistically describe. And we see that basically we are not sure that we need to use exactly the same general tools to describe these physical fields than for standard classification tasks. And the question will be, which representation do we want to use for physical field? These physical fields I showed to you are smoother than dogs and cats, so we expect them to be simple, or at least simpler. So the question is, can we take this simplicity into account? And can we add this simplicity as a prior to the statistical description? And you see, that's a question that is a little bit tricky because I said to you that these fields are simpler, but I didn't explain to you exactly what it means. And to define exactly what this simplicity is already a big problem. We can say that this field can be described by a partial differential equation or things like that, but it's not easy at all to encode in the statistical description. And the main thing we want to keep in mind is that basically, maybe we cannot describe exactly what are these physical fields, but we know which kind of physical properties we want to describe. And these physical properties should guide the construction of the statistical description, which means that, in fact, maybe encoding the prior in the description is to have a statistical description for which all the physical properties are easily readable. So the idea is that the statistical description should also simplify the description of the physical property. And if we success in this small loop, maybe, in fact, we was able to encode some of the priors we want in the statistical description. A huge question that arrived at this step was what exactly need to be machine learned? Because we want to study fields for which we don't have any models. If we have a model, we can devise an estimator related to this model that can be optimized, and often it's the best idea to go. But if we don't have any model, at which stage should we begin to make machine learning? We need to make machine learning, but at which stage? And do we need to machine learn the representation? If we don't, or at least if we first don't want to learn too much from in the machine learning sense, but want to encode the prior, or to include the physical general prior. So that's all this kind of question I will discuss about, and this led us to the reduced wavelet scattering transform I will present. It doesn't mean that it is a solution to do. It's a first pass to try to answer this question, but I think it's already a first guess of what we should do. So to begin with, I will present the WST, the wavelet scattering transform from Stefan Mala and collaborators, and apply it as an example to physical field. And it will give us an idea of what this simplicity I was talking about is. Then I will explain how we can build the reduced wavelet scattering transform, which is the representation we are discussing about, and which is based on the WST, the wavelet scattering transform. And then we will show what are the prospects of this transform and what question it raises. So the wavelet scattering transform is based first on the wavelet transform, which is a very efficient way to doing a multi-scale hierarchical approach to describe long interaction, as Stefan Mala discussed. So the wavelets we use are Morley wavelets in 2 dimensions. So they are described by an oriented scale, J and theta. We will use discretized wavelets. So J is related to the absolute size scale we are considering, which is 2 to the J, in fact, as we can see in the Fourier spectrum. And theta is an angle with respect to reference angle. So you can see all these wavelets probe a particular region of the Fourier plane. So here you have the first wavelet and its support in the Fourier plane, the second wavelet and its support in the Fourier plane. We can rotate the wavelet, it rotates its support in the Fourier plane, and we can delete the wavelet, and it will also delete, or rather translate also, its support in the Fourier plane. Here we choose to consider 6 scale and divide the half plane at 8 angle. It's the choice we did. And we will follow this convention for the whole talk. But it means that our wavelets are able to sample the whole Fourier plane up to the size 2 to the j. Here, it will be 32 pixels, in fact. So the wavelet scattering transform is based on a hierarchical multiscale approach from the wavelet transform. It has a reduced variant. It can moment of order up to 4. It does not necessitate any training stage. So that will be at our starting point. So I will discuss it in a lot of detail, but I will rather present how to compute its coefficient. Stefan Mala talked about it Monday. But what we have in mind is that even if it was, this representation is not trained, but it is able to have very good result in all standard, simple, let's say, classification tests. It means that it's not completely efficient if you want a very complicated training set with cat, dog, and so on, but maybe that feature we don't want to encode in physical field. So it has already almost state of the art. It has a hierarchical structure with 3 layers of coefficient. You can see its construction in the same way as with a 2-layer convolutional network. So the first layer encodes the mean value of the field. The second layer, the first layer encodes the amplitude at a given scale. So it depends on one oriented scale, G1, theta 1. And the second layer encodes the coupling between 2 scales. So these are coefficients that are labeled with one oriented scale, G1, theta 1, and the second oriented scale, G2, theta 2. And if we choose to describe 6 scale on 8 angle, we have around 1,000 coefficient, which is already not that much, actually. So to compute the WST coefficient, we assume we work with stationary process, so we can make integration of the whole image. So from an image, A of R, we can do just the integration of the image to have the mean. It's the 0th layer as 0. We can filter the image by a given scale, by doing a convolution with the wavelet at a given oriented scale, G1, theta 1. We take then a L1 norm, a modulus. As it's a convolution, we have one image for each G1 theta 1 oriented scale, and can make an integration to have a coefficient. So we have one coefficient for each oriented scale. And then we can do it again, and we can filter the map we had previously by a second wavelet, J2, with an oriented scale J2 theta 2. So we have one image for each pair of scale. We can integrate, we have the coefficient, S2 of G1 theta 1 and G2 theta 2. And to understand what it means, when you do first convolution with a G1 theta 1 wavelet, you are filtering in the image this particular oriented scale. Then you take a modulus, which means that it's a nonlinear operation. And what it will do, it will basically erase some part of the oscillation. So you will just localize where are these first oriented scale. And by doing the second convolution with a wavelet, you will see at which level the first J1 theta 1 oriented scale is convoluted, is modulated, by the J2 theta 2 oriented scale. So let's show what it gives when we apply this kind of description to physical field. So we consider several examples. I will only give 2 simple cases, but we tried also on even observational data from the Herschel satellite, and it works very well. But what I will show to you is 9 sets of 20 maps from turbulent magneto-hydrodynamics simulation, which possible large-scale magnetic field, which are done by people at CEA, Cedric Collin, Patrick and Bell. And we will use also 9 sets of 20 synthetic maps of fractional Brownian motion processes, which are basically Gaussian fields. Here an example of what we have. So you see that the fractional Brownian motion map, Gaussian field, we can increase the Earth exponent, which is, if you want, the power law exponent of the Fourier transform. And here, several different cases of MHD simulation. Here, the B field, the magnetic field, has an increasing strength, but there are also other physical parameters, as the turbulent forcing that I didn't show there. But you see that we have very different kind of map. And here an example of J1 theta 1 coefficient in alphabetical-graphical order, lexicographical order, sorry. So to see how they work, depends on J1, the scale, and theta 1, the orientation. So that's an oriented scale. I have 48 coefficient with 6 scale and 8 angle. And here I have 1 column for each value of J1, and in each of these columns, you have the 8th value of theta 1, okay? Same here. And what you see is the fact that it is simple. I mean, we don't have very complicated patterns that appear. We are able to identify what happens. For example, for the fractional Brownian motion process, we have a process that is isotropic, so we shouldn't expect this coefficient to depend on θ1 at fixed J1. And that's basically what we see. We have small defect due to signature of the lattice that appear at the smaller scale and the larger scale, but basically what we have is only plateau at fixed J1. And if you consider the MHD simulation, we have this initial contribution with a plateau, but we have additional modulation with the angle. But we see that these modulation have a very informative feature. Basically, they are not random oscillation. I make appear a particular favorable direction, and it's in our plane just a dipolar modulation. That's quite simple, and we see that it's the same kind of angular modulation that appears at all the scales. The amplitude can be different, but the reference angle is the same. So basically, I was speaking about simplicity. Here we can see the simplicity. We had 48 coefficients, we could have whatever we want. It could be very complicated. If you consider an image of cat, dog, it will be something which will be very, it won't be like that. So, c'est bloqué. It's blocked. I cannot use the. Cannot use the remote anymore. Okay. Yeah, but there is just a screen, not my computer. So the idea is that there's a new receiver detected. Okay. So the idea is I will show you the same kind of images for the plots for the S2 coefficient, and we see that there will be the same kind of regularities that will appear. Basically, most of the discussion here will be about the first layer of coefficient S1 because they are much easier to understand and to look at. But we can do similar consideration for the S2 coefficient, and these coefficients are very important because they encode a lot of information. And to be able to make this reduction for the S2 coefficient, even if they are less easy to understand, is what encodes most of the information we need about the non-Gaussian processes. It does not work. Okay. 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 We will discuss that thereafter. But like, okay, my screen is frozen here, but I have to look at this one. So here, example of S2 coefficient. So second layer, so it depends on 4 coordinates, J1, θ1, J2, θ1. Here is for fixed J1, okay? You see the 8 value of θ1. Here are the values of J2. So what I didn't say is J2 has to be larger than J1 because you consider a modulation at a larger scale. So J2 has to be larger of J1 than J1. And for each value of J2, you have 8 angles. So you see you have a pattern which is much more complicated than in the S1 case, but we recover that it is quite it has a lot of structure that could be understandable. And you see, here we have something that is isotropic, and we see that the level of all these modulation seems to be the same for all the θ1. And for example, if you consider the case of a MHD simulation, which is anisotropic, we recover. So the patterns are clearly different, but these are understandable patterns. And we see that the level of anisotropy is also seeable here. And we see that we have the direction of anisotropy that appear, which is more or less the same that we had for the S1 coefficient. And we can do the same for all the scales. So here there are all the values of G1. I won't enter in the detail, but we have some structures that appear. And this kind of structure is the simplicity I was talking about at the beginning of the talk. So to show to you, to identify this pattern is just with broad word, I have an isotropic term, which is just a function of J1, that's the plateau we was identifying. And I have an anisotropic term. I already spoke a little bit about them, but that's the same angular function that appear. Find a favorable direction. So for example, if we take the same simulation, but we make a rotation of this simulation, we expect this favorable direction to be modified. If you modify the large scale magnetic field, this favored direction will be modified, but we understand what it is. And the amplitude of this modulation depends on the angle. So that's what we encode in a very simple way, actually, in the reduced wavelet scattering transform. So these regular patterns, we will describe them by specific angular modulation. This specific angular modulation will be encoded in the reduced scattering coefficient, and the huge step that is done doing that is the separation of these different angular modulation, which are understable and which allow to identify specific physical features. So the WST information will be distributed into only a few terms whose physical meaning is identified. We was talking about level of anisotropy, direction of anisotropy, and so on. So we did that. I will show you how we can do that very simply. And also if it was successful. Actually, it works on all the data we had. And when we extend it, we tried this fit to other kind of data on which we didn't learn, it also works. So it has been proven to be very predictable, to have predictivity, sorry. So which angular dependency to expect? We work with the logarithm of the WST coefficient, so we factorize the different angular modulation. So here for the S1 coefficient, we have one isotropic term that doesn't depend on the angular term, and we can add several, if necessary, angular modulation that will depend on the scale and on the angle. And basically, the angular modulations, they are given by their dependency on periodicity. For example, if I have a favored direction, I will have θ1 minus a θ that defines this favored direction. And I will have a periodicity of pi. If I have a signature of lattice that appear, I will have just θ1. If I say that θ1 equals 0 is aligned with the main direction of the lattice, and a pi over 2 periodicity. This kind of identification of feature is very important to distinguish the different physical terms. And basically, when I say that, I can do a Fourier series if I want. Let's consider the simplest case. I will consider simple cosine dependencies to begin with. And here it's what I said. If I have isotropic dependency, it cannot depend only on θ1 and θ2, but in θ1 minus isotropic. We can consider pi periodicity. If I have an isotropic dependency, for example, in θi minus θ reference, with pi periodicity, that's what we expect for a large-scale magnetic field. If you have something which is related to a lattice, we expect to have a, okay, I already said it. So that's the RWST model. For the first layer, we just have an isotropic term plus the anisotropic term I was speaking about. And for the second layer, with one direction of anisotropy, which can be, for example, related to a large-scale magnetic field, I just have a constant term, an isotropic modulation that, in fact, we understand to be related to the presence of geometrical structure in the field, and to anisotropic contribution. So we arrived to a few functions. Actually, you have also the angle, but it was not very good if I put boxes on them on this slide. And all these functions are what is called the reduced wavelet scattering transform, RWST. So here an example of fit on 20 2 to the 8 2 to the 8 turbulence simulation maps. Here you have the residual error, and you see that it works very well. So I won't enter in the details of what we do physically with it, because I want rather to discuss the interface between machine learning and physics, but to give you some example, it helps us to, in the map, and is the cases we consider it helpful to identify physical features through the scale, because all the reduced wavelet scattering transform coefficient depend on the scales, okay? For example, it was able to identify the isotropy and the anisotropy. If we have a process that is isotropic, all the anisotropic coefficient vanish. So we can very simply identify this contribution. We can have scale invariance. We know which coefficient, we know the signature of scale invariance for the first and second layer of coefficient. First layer, we need to have power law. The second layer, we need to have functions that depend only on J2 minus J1, the ratio between the scale. So we can identify, for example, that the isotropic coefficients are mainly scale invariant, but that the anisotropic coefficients are not scale invariant. We can look at the degree of coupling between scales. We can look when the scales strongly decouple, when they are coupled on very long range. It can be related, for example, to the presence of geometrical structure in the field. It can be related to some notion of intermittency. And as I said already, so I won't discuss it a lot, it can identify signature of different processes. If I have a large-scale magnetic field, I'm able to detect it. If I have a lattice, actually, we had simulation where there was a signature at the lattice at the smaller scale, we basically should expect, but we was able to identify this lattice signature to identify their level, at which scale they appear, at which scale they didn't appear anymore, and so on. And also the structure of the coupling through the scale is very interesting. For example, we was able to see that a large-scale magnetic field does not have at all the same signature that in terms of anisotropy that an emergent anisotropy just from the spontaneous symmetries breaking of the nonlinear dynamic at stakes in the MHD. And for example, we was able to see that these kind of signatures are very different. And for example, in the Herschel observation we studied, we saw that the signature of anisotropy was completely different than the one for MHD simulation with a large-scale magnetic field. But it was rather a self-induced anisotropy. So to give you an example, but quickly, you have the S1 coefficient, the one I discussed in this talk because they're simpler to show. Fractional and Brownian motion, 4 different Earth exponents. You have 4 different classes of MHD simulation. Here we recover the parallel through the scale for the Power spectrum of the that we have isotropy of all these processes, anisotropic coefficient are 0 up to the error bar. Pay attention that the scale are not at all the same. Here the angles are completely random because basically as the amplitude is 0, it's very complicated to fit in those. Here we recover the MHD simulation. Pay attention to the large scale to the right. So we have the injection scale, the turbulent cascade. We recover different signature of anisotropy. The red simulation has a very large magnetic field, so we can see very strong signature of anisotropy. As a small large-scale anisotropy, the two other do not have large-scale anisotropy, but we saw that they have spontaneous anisotropy. We recover that the signature of anisotropy are very different, and note that these are only the first layer of reduced scattering coefficient. We have also the second layer, which is much more richer, and we recover different direction of anisotropy. And we was also able to do synthesis. So as we consider scale up to 2 to the 5, actually, it doesn't encode, our description for the moment didn't encode the large-scale modulation and didn't encode, for example, the long thin filament. But we see that with only 20 maps and less than 100 coefficient, actually even 50 because you are not able with naked eye to see the anisotropy features here, we are able to encode a lot of information about the don't have the large-scale modulation, but fractional and Brownian motion are very well reproduced. And you see, up to the large-scale modulation and the long thin filament, all the MHD simulation are very well reproduced. So to conclude quickly, the prospect and open question. So we saw that we was able to make the reduced wavelet scattering transform and to apply them to physical field. It has a strong reduction of dimension, a factor of more than 10 from the WST coefficients that already don't are very numerous. We was able to identify physical features, and it can be extended to other fields in the WST framework. I mean, we try it to new field, it works. If necessary, we expect to be able to add other terms if we need to understand other kind of anisotropy, for example. It's very natural. And it comes from very general consideration. We don't have any specific model. We should be able to apply it to a very lot of different kind of fields. And this was the consideration of simplicity I was talking about at the beginning of the talk. And we have some strong points for cluster reduction. So it can be computed without any training stage. It gives strong constraint of the WST coefficient and also strong constraint of the WST covariance. So I will just use 1 minute to explain that. So basically, you can see that as a sparse representation for physical fields. Or in other way, you can see that we identify in the whole WST space a surface on which we expect the physical field to be. Okay? So it means that we can make an efficient extraction from noisy or limited size data because we have a point in the WST space and we can project in the surface on which we expect the physical field to be. And also, we see that we have reduced wavelet scattering coefficient, which are very continuous. It seems to be very continuous function, so we can make super resolution at small and large scale, and it can help us when we have observation at very reduced range of scale. And also, it's a strong constraint of the WST covariance, because here, I have coefficient we showed in the talk, and I can also describe the covariance, but you will see that a coefficient of close angle are related, so they have a non-vanishing covariance, but it won't encode all these dipolar modulation on the plane. I will have some bulge here, some bulge here. When one of them will move, the other will move, but it won't be this particular structure. In addition, a covariance is not able by itself to separate the constant term to the angular modulation, which for us is very natural. So basically what it means is that when we want obtain new realization of WST coefficient, for example, to do new synthesis, what we do is we can displace ourselves in the surface of physical fields that we define as the WST coefficient. In terms of simplicity, I was talking about, we know that when this coefficient will be modified, the isotropic level will be modified, the amplitude of the anisotropy will be modified, and the favorable direction will be modified, but you don't want to modify all the coefficients independently. Finish in 1 minute if I can. All these points are particularly useful when a few amount of data is available, because we cannot brute force machine learning. In astrophysics and cosmology, as François Boulanger explained, when you have one sky, okay, we have several channels, but when you have one sky, so the more priors we can put in our representation, the more efficient we can be. As open question, why does it work? Because actually it's amazing that such a simple decomposition works that much and is able, for example, to do such good synthesis. So we work with two-dimensional fields. We cannot extend that to first-dimensional field, or even we could think about doing that in 3D, but in more it could be complicated. We work with stationary fields. Actually, to extend that to non-stationary statistics as in observational data is much more complicated. And it works maybe very well because we use the WST, which seems to be a very natural tool to do physics. Thanks to its hierarchical multiscale approach, its efficient separation of angular and scale dependency, which is related to the use of the wavelet, and to the fact that the WST coefficient seems to have very continuous behavior, which can be related for the fact that the WST is continuous, for example. So could we apply it to other representation? It can be expected. Actually, it's all in the link with physical properties that should be simple. I discussed it at the beginning. And actually, we did 4 tests with the fixed harmonic transform that Stefan Mahler has been developing since a few years, and it already has been successful. Even if we didn't do it completely, but as a first test, it works. So last point, maybe there is something there which is a generic stochastic model for physical field. So is there a stochastic model there? The first approach could be, for example, a hierarchical scale modulation model. We have the large scale, therefore spectrum. We generate the small below, considering their modulation with the larger scale. Then the scale below, considering the modulation with the larger scale and the less than larger scale, and so on. So the idea is that it could also be successfully improved by considering complementary representation at which we do this kind of reduction. And I finish. It could give a simple and general framework for such problem. And here are okay, that's the same thing, but in one slide. Thank you.
One of the assumptions here is, well, you're looking at homogeneous fields.
So you have two kinds of homogeneity. You have the fact that the statistical properties are homogeneous and that the field is homogeneous. In terms of when we have field with a huge dynamics, often it's very useful to take the log and then to apply the statistical tool to the log. Actually, that's what we did for the MIT simulation. So we hope we can solve this problem this way, even so it's the first answer. And considering the fact that the statistical property can vary from one point to the scale to another. Actually, so it's my last point. And what we believe is that this reduction is very efficient when we have some homogeneous statistical property. So to deal with non-stationary process, we expect to do in 2 steps, to be able to distinguish mesoscopic scale, if you want, on which we can estimate that the statistical property is homogeneous, and then consider all the reduced WIT coefficient vary on larger scale. And for example, to be able to link this variation of the reduced WST coefficient, the statistical property at the microscopic scale, to larger scale physical parameters, like large scale magnetic field density, and so on.
Right. A lot of these processes are fluctuations are different in high density.
Yeah. So, but this has to be described for our point of view by the fact to include larger scale on which the statistical properties themselves are modified.
The statistics for the density field, is that right, in the MHD example?
Yeah.
Have you tried to synthesize like vector valued fields, like the velocity field or the local magnetic field?
So that's a very good question. Actually, Bruno will give a talk today, normally, on which he will explain how we extended this kind of consideration to two-dimensional fields, vector fields that are the polarization Q and U fields.
Well, in order to answer your question and to fit in talk before lunch and move the long talk after lunch, Bruno will actually speak next.
So we believe it won't be that complicated, even it can be a little bit technical to generalize in 3D. But I mean, we have the idea to do that. We know to distinguish direction in 3D. We know to generalize just the simple cosine function in 3D with projection and so on, or just harmonic tools in 3D. For more than 3 dimensions, it could be more complicated or at least more technical, and I'm not sure we want to do that because we could lose the simplicity that appears in this coefficient. But yes, such thing could be generalized. Simply, I would say directly in an evident way in 3D and more technically in more than 3 dimensions.
Thank you.
Thank you.